29 moons. There is a spirit like me and you, stretching across the universe, connecting me and you. Electromagnetic worlds, stretching across the universe, connecting me and you, connecting me and you, all the way across the universe, all the way across the universe.
Hi, this is Rick Maltese.
And this is Mike Conley.
For decades now, the naysayers have been saying that nuclear power is a dead end and that the nuclear renaissance is a dream, or even worse, a delusion. We will be talking with the pioneers in the field that are taking it to a new level and proving the naysayers wrong.
What we are talking about is reactors that not only incinerate nuclear waste, but turn it into energy while doing so, and doing it cheaper than anything in existence. We're talking about reactors that are both walk-away safe and mass-produced in factories. In short, we are moving fast towards the atomic revolution.
With us today are Ed Pheil, the Chief Technology Officer and founder at Elysium Industries. He has been designing reactors for 32 years, including for the NASA space program. Lars Jorgensen is one of the lead architects of the ThorCon molten salt reactor. Lars is a lead technical contributor to the Thorium Molten Salt Reactor Public Forum. Rory O'Sullivan has a background in mechanical engineering. He is a former advisor to the International Atomic Energy Agency on molten salt reactors and is presently the CEO at Moltex Energy. Gentlemen, welcome to the show. How close are we to the dream of super cheap nuclear power, and how low of a price can we expect to see?
I think that we will have low-price nuclear power before the end of the decade. As far as the start of rollout, it will take a number of years to build out enough reactors at a low cost to really get that far. And as far as low price, I think we all think that we can compete with natural gas at its prices that it is today.
This is Lars, and from our vantage point, we expect to see initially around 3 cents a kilowatt hour at the cost line and dropping over time as competition heats up. We do expect this by mid-decade, so around 2025 we should be starting commercial operations and be able to ramp up very quickly.
Rory O'Sullivan here, Moltex Energy. So really, any major infrastructure project in the past has taken about 8-9 years. Today's nuclear projects take about 12 years. It's about 2-3 years pre-project work, about 3 years licensing, and then 3 years build for these advanced reactors. Typically, today's nuclear will be about 5 or 6. Looking at cost, for our main reactor, about 1,000 megawatts, we're looking at $2,000 a kilowatt. So that's about 2/3 of the cost of coal plant today. If we configure it as a peaking plant, you get down to around $1,000 a kilowatt, or $1 per watt, which is comparable to gas on capital costs.
There are many different designs for advanced nuclear reactors. What's the basic differences between them, and can someone give us an overview?
It's a difference not only in the design, but also in the market approach. So from ThorCon's viewpoint, we are targeting the developing world, particularly Southeast Asia, trying to go for high volume and low cost. In our view, we're targeting a thermal machine because we believe that's the quickest to build and the easiest to operate. But it does not focus on minimizing waste. The waste is already very small, being 100,000 times smaller than coal. So we're not focusing our efforts on that part of the problem. We're focusing on cost and schedule.
This is Ed Pheil. As far as types of advanced reactors, there's many different kinds that are actually viable. The liquid fuels give you a dramatically lower fuel cost relative to solid fuels, because solid fuels get damaged over time. You have to constantly replace them because of the manufacturing cost of those solid fuels, but also things like safety issues. The heat is put directly into the liquid fuel, and you don't have to have a heat transfer in the core and then worry about losing the coolant from that. So you have a lot of safety systems associated with that. If you lose pressure for gas or water, you lose your coolant. And so those have associated cost systems that you don't necessarily have with a molten salt reactors.
I feel we've been observing some of the negative things about the industry, but we haven't praised fourth generation reactors, what their possibilities are.
Each technology has different advantages. The common ones are when you're operating at higher temperature, you can use high temperature heat industrial applications. You can also store the heat so that you can use the reactor as a peaking plant. The ability to use spent fuel and actually burn the original waste.
I think from our vantage point, the big steps forward are being able to compete directly with developing world coal costs and full passive safety. For our reactor, we're planning on building it completely in a shipyard. We can get a fixed price contract to have the reactor finished on schedule in a 1-year build time. And volume. We can build 100 gigawatts worth of new power plants a year if there is the market for it. And just the surplus capacity in the shipbuilding industry amounts to on the order of 200 gigawatts of power plants a year. So that the capacity is there to be able to churn them out like we churn out wide-body airplanes, which is quite in contrast to the light water reactors where you have the high pressure and the need for a very specialized forging, which there's only a handful of places in the world that can be done.
You can put these molten salt reactors directly on ships, and that requires a huge political lift to get all the countries around the world to let those into port.
Ship lifetimes aren't all that long. They are very recyclable, so I would expect that you're going to design new ships with nuclear reactors and that we will not be retrofitting existing ships, but rather building new ones.
How far away are we from a mass-produced nuclear reactor, and how much of a game changer might that be?
I'd say that given the right politics and right financing, we could be into mass production within 6 to 7 years. And how much of a game changer that would be? It would be as big a game changer as when we shifted from coal to oil for transport. This is a less often than once in a lifetime change. This is a once in a couple of centuries type change that would have a dramatic impact on the entire world.
These revolutionary reactor designs have been around for a number of years. Why haven't these designs taken over the nuclear market?
Basically, there's a lot of fear that was put forth. People were afraid of nuclear weapons, and they used that fear to drive a wedge against nuclear power.
I'd say it's also a reflection of the way regulations are done. Because of the massive safety concerns, the procedure in the U.S. basically is you have to first prove that your plant is fully safe to run for 40 years at full power, and then you're allowed to start breaking ground. But in order to prove it, you have to have test results from a reactor, but you're not allowed to build a test reactor because you can't prove that it's safe. So since we stopped building test reactors back in the early 60s, it's been very, very difficult to do anything different. And if you look at what we've done different since the mid-60s until now, the changes are very, very minor. Coming in with a whole new design in the U.S. regulatory system is just not possible with the current rules. You'd have to be willing to build a $1 billion plant with the guarantee that you're never allowed to charge anything for it, never get paid at all for it. That's a pretty tall order and something that private industry is generally not going to go for. So the long investment times and the way the rules are structured in the U.S., it just makes the whole process very, very difficult. There isn't that danger.
The software industry, return on investment in 3 to 5 years, and with the regulatory requirements for licensing and the time that it takes to build a complex machine, you can't get a return on investment in 3 to 5 years from initial investment. So that makes investors leery of investing in a long-term project where they have to take 10 years or more to get a return on investment.
And then you add the political risk where even after they've finished a power plant like Shoreham, the politics might change and now you have a plant that's been built but you're not allowed to use.
Other than not changing the rules, what else could be done to speed up licensing?
Today, the regulation and the licensing process we have is due to public opinion over the last 3-4 decades, and that's a consequence of the various accidents we've had in the past. It's that structure that's led to the incredible safety performance that the industry has today. Now that we're moving towards a different paradigm in safety in nuclear, and we can go from a intrinsic hazard with a lot of engineering components to increase the safety to inherent safety in the first place, so you don't need that complexity, we can really look at simplifying the process moving forward. And there's really 3 main components to that. The first one is the government's role. It's making sure there's the right framework in place and informed regulators on the new advanced solutions. The second one is simplest to say, the hardest to do, putting more regulators on it, putting more design teams to get it through the system faster. And then the third one is often overlooked at the early stage, but it's a harder one, is getting public and local support, particularly around a project. If you have a huge swell of local support around a project and you don't have interveners and people complaining and making comments about the process, it really smooths the whole thing over and makes the regulator's job easier. As we demonstrate safety on these new reactors, and we understand that there potentially is no hazard to low-dose radiation, when that knowledge base is available and very clear, that we're going to really be able to dismantle and simplify the regulatory process to bring it more in line like an aviation industry. Almost all of our effort at the moment is going into planning how we can simplify the licensing process here in Canada and do it as quick as possible.
I don't want to push it all on the regulator. We do need experienced people, and that means we need people going in and coming out of universities, and they need to know more than just water reactors. They need to have advanced reactor skills coming out. There's a lot of comes out in the advanced reactor with PhDs, but you also need the undergraduate to be introduced to advanced reactors as well. At this point, we don't see that. The United States exported most of their manufacturing to other countries, and they're bringing it back, but they're not bringing it back in the form of skilled labor doing things like welders and electricians, specifically in the nuclear field, because nuclear welding, for instance, is a specialized technique.
I would also say that the design has a lot to do with it. So if you have a design that is fully passive, which I believe all 3 of us do, then enormous portions of the power plant are no longer safety critical. So, for example, I know for ourselves, and I expect for the others, that we can take a full station blackout and not have any risk of a release. If that's the case, then the whole diesel generators, battery backup, century turbines, dual connection to the grid, all of that is no longer safety and is no longer in the purview of the regulator. Likewise, if you're impervious to operator errors. Likewise, if you don't depend on complex machinery. If you look at the safety systems for light water reactors, they're pretty complicated because they've got to overcome this enormous pressure. And when you don't have that enormous pressure to overcome, then a lot simpler and more passive, just based on physics, safety systems are sufficient. And it makes the regulator's job to review it both much easier and therefore shorter, but also much safer. If you have a very complex system, the chance that some combination of events causes a problem that you didn't anticipate go up.
The cost of licensing is enormous. I wonder if you could give some background, a little bit about what it actually costs to license getting a reactor built, and why does it need to be so expensive?
I'll just give you a prime example. It costs NuScale $500 million to submit their license before the NRC even started working on it. They expect it to cost about $1.1 billion, and that's for a very, very small reactor with a low source term and passive cooling and no EPZ outside the site boundary. And yet it's still taking longer than the NRC said it would take for a large water reactor. Originally, the NRC said it was going to be 60 months to license it. They backed off to 46 months. But The NRC claims that they can license a large water reactor in 39 months. My contention is if it's a low source term and it's passively cooled, you should be able to license it in much less time.
Can you explain to listeners what a low source term is?
A low source term, that means that the density of material, if released, and we're not saying that it is released, but if it was released, would not go very far and would not be a high density. It would not cause a lot of health problems. For example, the 3 reactors at Fukushima, they had a huge source term. All 3 reactors released radioactive material, yet no one was harmed. And now you say, well, we've got these smaller reactors like NuScale that are down around about 160 megawatts thermal compared to 3,000 megawatts thermal. Therefore, it has a very much lower possibility of hurting anyone. But yet the regulator doesn't account for that. There is no reason under the sun that you can't license a reactor that is safer than a coal plant or a gas plant in the same time that you would license a coal plant or a gas plant.
On the question of cost, and NuScale is a good example we talked about. NuScale has some really clever passive features, and they've managed to get approval on having as we mentioned, a zero emergency planning zone. It's not eliminating the hazard altogether, which is what most of the 3 of us are looking to do. The EDF EPR, the big reactor that's now under construction, that cost in US dollars about $130 million just for the generic design assessment. Then the Hitachi project was about the same. So the numbers are big here, and what they all have in common is the complex safety systems that are required to maintain the level of safety of the plant. It's when you can eliminate them, building on what Lars was talking about earlier, you can eliminate the high safety class 1 components and still get the same level of safety, is where you can really reduce the licensing cost and the cost of construction and manufacture of these components.
If you have a developing country, they may insist on a design license from a quality regulator before they'll build it. And I'm not saying that they'll all require that, but that's something that may be expected that somebody else will want, like a U.S. or European type license before they'll build it in their country. What happened to TerraPower, they were developing the sodium reactor in China, but China was requiring them to get a U.S. license before they would build the reactor in China. But most of the countries that need nuclear power these days don't have an experienced regulator. China is fairly experienced, but they're still asking for a U.S. license.
And no one in the world has an MSR skilled nuclear regulator. No matter where you go, they're going to have to figure that out.
That's correct.
Does the NRC take into account new designs? Are they able to make that leap? What a new reactor has to do the same regulations as an old reactor?
I'm actually on the committee that is trying to write generic design guidelines for molten salt reactors. The current rules are written presuming a light water reactor and has a lot of rules that are very specific to that. They recognize that this is outdated and they are working to change it. They hope to have it changed by sometime in the 2030s. So it's a slow process, but they do see that they do need to change.
The NRC has had the DOE write some initial guidelines or recommendations to the NRC, which the NRC is acting on for liquid metal reactors specifically and gas reactors, because the United States has built those for decades now. There's like 50, 60 years of experience on those. So the DOE was able to write some recommendations for guidelines for the NRC, but they don't really have that for MSRs.
Well, actually, some of them are being adapted to include MSRs. So like functional containment was included in the regulations as a generic thing, so it did include MSRs, and that rule did make it through the NRC. But there's a long road to go and a lot of bureaucratic inertia to overcome. It'll take a while.
They don't understand molten salt reactors, so it's hard for them to figure out what the regulatory requirements really should be, which is why they're having A&S and commercial industry people work on the basic regulations.
There's a number of people that have expertise that, if they were hired by the NRC, could make good recommendations. Now, the funny thing is, they're not asking for people with those kind of experience to join, are they?
I think the NRC is faced with a declining budget, not an increasing one. So I haven't heard anything about them hiring more.
And if you're asking about talking to people that are on the forum and stuff like that, a lot of those people are actually in the commercial industries, and the question of independence of the regulatory comes into question at that point.
In these communist countries, that's not an issue. They are willing to put any expense out. But in North America, it is an issue.
That brings up an entirely different area of competition. In the United States, industry is commercial. It is not government supported. Russia and China are definitely government supported. So we are competing against government.
I think it's a reflection of the fear of nuclear that today in the U.S., you have to prove absolutely that your reactor is safe before you're allowed to build it. You can't even build the test reactor reasonably. And that makes it so that you have to do all manner of substitute experiments where you're trying to test out one thing versus another and then test out a combinations of things. But it makes the whole process take a very long time. Does it have to? No. I mean, we built them a lot faster in the late 50s and early 60s. We got through that process and built the first ones. We built a lot of different kind of reactors in those days. We just have gotten very timid since then.
Right, and I might add that Idaho National Lab is trying to focus initial prototype builds at Idaho, which is kind of a remote area. They're trying to figure out how to get back to that fast build, fast testing. That's not really happening with NuScale, but Idaho National Lab and ZOENE are trying to figure out how to get there, but they haven't figured it out yet.
Well, I have a suspicion that this concept of ratcheting has been at work. Because of nuclear fear, once a regulation is established, it becomes very difficult to reverse it, even when technology eliminates the reason for the regulation. Senator Cory Booker recently offered an analogy about our outdated nuclear regulations, and the analogy is, what if we still had a requirement that pilots wear goggles? And I think it's a good analogy, and it seems that that's what's happening in the industry. So I guess my question is there a challenge with advanced reactor proponents to convince the NRC that some regulations just simply no longer apply, rather than showing how that regulation is fulfilled? Two different things.
Yeah, ratcheting, pretty good word for that to describe the process. If you look at history, really what you had originally is you had typically solid fuel reactors, water-cooled reactors. Generally, there is an intrinsic hazard. And over time, we've added features to mitigate that hazard and to reduce the overall risk. That's been as the reactors have got more complex, like the EPR and the AP1000, and regulations have got more complex at the same time. But today, we're all approaching it quite differently. We're looking at eliminating that hazard altogether. In our particular case, we can't come up with an accident that has a large radioactive release beyond the site boundary. But it's going to be a big challenge for regulators to just trust us. So yes, it is a monumental challenge to get there, but really the only way to do it, to influence the regulators and the public, is to actually go and get one of these or more built, demonstrate the safety, build that confidence, and it's then you can actually start taking down some of the barriers. You need a regulatory framework that can enable that in the first place, but then to really simplify that, you have to have that trust. We've avoided the US almost entirely up to now. We have had no presence there, and that's primarily because of the complexity with the Nuclear Regulatory Commission framework, the prescriptive requirements. But now, as we see this momentum build, the NRC are moving at incredible speeds for a regulatory body. Maybe they're going to move a little quicker after all.
There certainly is a growing political pressure for the U.S. to move quicker, but you've also got a big bureaucratic inertia, and you have people who don't want it to move quicker. Part of the problem is that you've got active opponents in some of the misguided environmental groups that view nuclear as being even worse than coal, which is quite amazing to me. And you've got established industries in natural gas that want to try to throw any roadblock they can in the way of a nuclear renaissance. So they do slow the process down. If we go overseas, where the choices are more stark and people have seen the results of China going heavy into coal or India, then I think they're forced to make a more realistic choice and say, no, is these dangers that you're talking about for nuclear actually real?
The United States sees that nuclear is being shut down and nuclear experience is being shut down. They see China and Russia building new advanced reactors and the United States not even knowing what that technology is in the future if we don't start building them. And if you think of it from a military perspective, they see them building, say, molten salt reactors on submarines or on islands in the South China Sea and listening posts that strategically you don't have to refuel or resupply, that the United States has a tactical disadvantage. And so the military in the United States is kind of scared that we're going to lose the capability of responding to either Russia or Chinese military capabilities.
If you have an MSR design that is functioning, what then becomes the necessity to have a small mini light water reactor? Doesn't that design become superseded by a molten salt reactor, rendering reactor design unnecessary or obsolete or outdated?
The light water small modular reactors are really an evolutionary design of what's been done before, and they certainly have some good improvements. The molten salt reactor are a revolutionary design. They're a step change in what nuclear can really deliver. They're a new paradigm in nuclear. We're all expecting that the economics will be lower than coal, and if that's demonstrated to be the case, then the role for small light water reactors, I believe, will be a lot smaller.
I think you will see different markets for different size reactors. So there are locations where they are remote, say an island, where they need only 30 megawatts of power. So in that case, a small modular reactor is really competing against diesel, and then the cost can be much higher and still be competitive. Whether that means a light water reactor or an MSR base, I think is yet to be seen. I think all three of us expect that we're going to beat the light water reactors in cost, and probably that includes for the small situations as well. But we're all on paper so far, and they've got real hardware, so there's sometimes a distance between paper and hardware. We'll have to see.
Mm-hmm. So I agree. One comment, though, they have built small modular reactors for longer than they built large reactors. Those initial reactors were built small and at lower cost, and I see the small modular reactors, the reversion back to small modular reactors, as a way to essentially bootstrap the nuclear industry in Europe and the United States to redevelop that supply chain and construction experience at a lower cost.
What are the potential problems?
So as far as potential problems, I think it's a new machine. We have to work through new issues. They're not particularly harder than the ones with light water reactors, but they are different, and so we have to figure out how to deal with them. Amongst those would be dealing with the chemicals, whether it's fluorine or chlorine, creating pumps that work at these temperatures. These are all what I would call engineering problems as opposed to basic science problems that good engineers, given some time and some testing, will work our way through it. But because they are new reactors, they will take a little time to work through those issues. I think the biggest problem with advanced reactors really is the social issue. We need to break through the idea that nuclear is somehow uniquely dangerous, when in fact it's uniquely safe. One issue that's often mentioned is the issue of corrosion. If you have molten salt at high temperatures and you get moisture in there, then it will corrode the metals very fast. But the truth is that if you have high temperature water and you put a little salt in that, that will also corrode things very fast. Clean water won't corrode as fast. Clean salt actually will corrode even less than clean water. So it's all a matter of keeping the chemistry well, keeping the redox potential in the right range, and keeping the moisture out. Those are all very manageable things to do. Metallic sodium does have a potential problem with fire. We've had a lot of metal sodium reactors around, and they've had a handful of fires. I think the danger from them is overblown. They've managed the fires that they've had, but it's a fire that you can't put out with water. But it does create an enormous social problem. That if you're an anti and you want to make a big fuss about a reactor, then you want to go and talk to a fire chief about how hard there are to put out, and then talk about how many tens of thousands of tons of sodium there is. My concern with sodium reactors is that it's too easy to create fear in the public's mind. If the sodium is combined, like sodium chloride or sodium fluoride, then it is not a fire hazard at all. Sodium chloride is another name for your ordinary table salt. Sodium fluoride is what you brush your teeth with. And those are the sorts of things that we use in our reactors.
What could we anticipate as a criticism to molten salt reactors above and beyond corrosion?
A common complaint I hear is that you have radioactive material moving in all over the place because we have a primary loop and we have a pump and we're moving the fuel. Instead of it staying inside of a little tube, it's moving around, which is not true perhaps for Rory, but for Ed and myself. To which I respond, it's at low pressure, it's inside, in our case, at least 3 gas-tight containers. Think of it as one fuel tube then. It really doesn't make any difference whether it's moving around through the heat exchanger or not.
People can visualize solid pellets in the core, they know where they are, they're sealed in the fuel assembly. With liquid fuel, it's a bit harder to visualize that stability and certainty that it's in a single location. But that's all manageable. It's engineering challenges. It's a social issue rather than a practical one.
Can they fall asleep on the job and suddenly wake up and realize that they should have been awake? Like, is that a problem?
I'm not sure about Ed and Rory, but my guess is it's like us, that if your operator falls asleep, you might have some damage to the plant, but you're not going to have any release. It just doesn't happen. So in that regard, I'd say it's a lot safer if our operator falls asleep than if one does, say, at a chemical plant or even a light water plant.
Or if they stay awake and do something stupid.
Well, how stupid can it get with a molten salt reactor?
So I'm going to guess that by the time we're said and done, a maybe not stupid, maybe a saboteur operator could manage to break our plant. But they're not going to manage to be able to cause a release to the public.
I also might note that we have 18-year-olds out of high school with a year and a half worth of training operating hundreds of nuclear reactors around the oceans today, and they operate perfectly safely.
How far have we gotten in terms of being able to turn nuclear waste into power?
Other people are focusing on that much more than we are. Our view is that the nuclear waste is a small problem and should not be focused on at the expense of cost or schedule. We need to really get the new generation nuclear out there and a mass-produced nuclear out there as fast as possible, because in the meantime, people are building coal plants. And once they're up, they're not coming down for at least 50 years. So I'd say this is not a critical, important question. It's one that can be answered even 100 years from now. It's fine to answer it. That waste is not big. We can store it, and it won't change over the next 100 years.
We have already converted spent nuclear fuel into chloride salt fuel, so we are trying to address that. I agree totally with Lars that you don't have to do that. This is part of the social image problem that nuclear has today, and so we're trying to address that as well. And the goal is to be able to demonstrate to the public that you can use that spent nuclear fuel, as I call it, stored nuclear fuel, same acronym, different meanings, and use all the plutonium, which is the part that people really try to use against the nuclear industry, but to let the public know that there is a solution, that waste that everybody is complaining about and using to hold up nuclear has solutions. And from an economic perspective, if somebody pays us to take the waste, whether it be plutonium or stored nuclear fuel, that's another income or revenue stream in addition to electricity or process heat. And so I think that will be a benefit to people. I mean, it allows us to use that fuel. The amount of energy in stored nuclear fuel from light water reactors is 30 times as much as the light water reactor produced. If you can show that as a positive benefit to the public, that you don't have a long-term waste problem and you can get rid of that fuel, that's a huge advantage from a public social license perspective. And then you can take the enrichment tailings and get another 8 to 10 times as much energy out of that. And as far as world supply of uranium, there's already enough out there to supply the world without mining for 10,000 years.
The anti-nuclear lobby, let's call them, it is the biggest issue.
It seems to me that this is a perfect blend that one technology can support the other. If large people are raising objections because of the quote-unquote waste that you're producing, the solution is put it aside and have Ed's reactor take care of it so that it becomes a non-issue. So it seems like both technologies are supporting each other, and that should handle any rational concerns. How do you guys view that as two products on the market that are basically supporting each other rather than in competition with each other?
You can do both systems. The thing that's holding us up from using the stored nuclear fuel and the plutonium that's already available out in the world is not existence of the fuel. It is just political access and social access. It's already available today. So we can do that right now.
From my vantage point, so I think it's very good for the world that we have several entrants taking very different approaches to see if one or more of them can cross the finish line. I would be delighted to be competing with Ed and have both of us have successful systems. That would be a wonderful outcome. And yes, we could definitely work together.
And I would be delighted to take Lars's fuel and use it in our reactor. I have no problem with that whatsoever.
But yeah, how economical is it for taking spent fuel and using it in a fast neutron molten salt reactor?
It's fairly easy to do. There's only one chemical processing step that you have to do. So what does that mean from an economic perspective? Pyroprocessing was 7 chemical steps, and we're taking that down to 1. We have no solid fuel manufacturing. The solid fuel manufacturing is 90% of the cost of solid fuel. So the economics are very good in that respect. And then you add on the fact that people are paying good money to store that nuclear fuel and that plutonium, especially in the United States. It's much more expensive in the United States because it's weapons grade. So the goal is to essentially use that as a revenue stream to offset the cost of conversion. And then our fuel costs are essentially either nothing or part of an overall revenue stream because we're getting rid of that waste.
Based on the economic modelling that's been done by Deloitte for us, we're looking at a saving of £7 per megawatt hour when we add in the cost of the conversion facility. The economics are really quite compelling on this, and it's a bit of a way off, but there's no major technical hurdles. The reason we can do this is we don't need the complex Purex reprocessing plants that cost multi-billions of dollars that needed in the past. It's essentially just converting from one form to the other, because a molten salt reactor, you can have a very impure fuel.
Molten salt reactors run much hotter than light water reactors, and I understand it is hot enough to do heat processing, in addition to producing electricity. This heat processing normally requires the burning of an enormous amount of fossil fuels to produce vital industrial products such as steel and cement. Could you speak about that?
Steel is typically about 1850 degrees centigrade. Cement manufacture is about 1450 centigrade. Our reactors are operating in the neighborhood of 700 C, which is well below that. So direct use of these reactors is pretty much in the realm of hydrogen separation, fuel separation, desalination, fertilizer manufacture as far as direct heat use. Now you can take these and you can add thermal boosters. You might be able to get up to cement manufacturing temperatures with that kind of a system, but I doubt if you can get clear up to 1800 C for steel. However, you do have a higher efficiency of electricity generation, and so you could use electric arc heaters, which is what they use to get steel temperatures now up to 1850, but use the nuclear heat to get it up to 700 C and use those other systems to get up to steel temperatures to displace the use of fossils for those systems.
Is that too much clouding up the issue when you think about using reactors for more than one purpose?
It's a common request to supply process heat in addition to electricity. I think, at least from our vantage point as a startup, we got to focus on one task, get that done, and then move on to the others after we've got the first task completed. But yeah, there are various industrial processes that could be used with the heat we have now. There are some that also use a lot of electricity, like in steel. Fresh steel takes a lot of heat, but when you recycle steel, that typically takes a lot of electricity. So we'd use our electricity directly for that.
And aluminum is a high electricity use too. The nuclear island, which is what we're working on, trying to drive the cost down in a light water reactor, is about 15%. Right? That's a nuclear steam supply. Reducing the cost of the nuclear part of the plant is not the whole picture. You have to also work at decreasing the cost of the rest of the plant, because if you drive the nuclear cost down to zero, you still have 85% of the cost. In liquid-fueled reactors, 90% of the solid fuel cost is the manufacturing of the solid fuel, not the uranium purchase or the enrichment cost. So now you're down another order of magnitude below the 30% of operating costs with liquid fuels. So the drive to maximum efficiency is not necessarily there, because you don't have to minimize fuel costs even as much as the light water reactor did. There's other options on the economics to drive down the cost of the nuclear plant to get going, especially if you're going into the process heat.
Expanding on that, a lot of the light water non-nuclear section is designed specifically and only for the nuclear plants. So a light water reactor typically will come out at around 300 degrees C. No other turbine for any other industry is going to be operating at that low a temperature. So they need custom designed turbines, and the whole plant is really custom designed, driven by requirements from the light water reactor. When we go to the higher temperatures, we look very much like a coal plant. So we can take advantage of all the vendors that sell coal plant steam turbines. And so we see much lower costs for the balance of plant because we are compatible with the coal plants and are looking at a much more competitive market. And because by the basic design, we've made it that the turbine and generator and all that stuff is not important to safety. And I think that's probably true for all three of us.
China was building, and probably still are, building 2 brand new modern coal plants a week. But they have already recognized that this fact that the coal plants and the high temperature nuclear reactors use the same temperature range of power systems, and the HTRPM gas reactor are specifically designed, once they start pumping those out, to go in and replace the heat source of the coal burning with those high temperature gas reactors, which we could do with molten salt reactors as well. That is why the HTRPMs are being designed for the sizes that they are. They are specifically designed for the size of the coal plants. So yeah, we're specifically designing it for the capability of doing either electricity or process heat in the same plant at the same time.
That's exactly the same as us. We produce high-temperature molten salt stored in large tanks, exactly like they do in the concentrated solar power industry. And then the customer can either buy his generic steam turbines, steam generators, or use the heat for another application. In terms of the difference of cost between the nuclear turbine and the non-nuclear turbine, let's say, as just roughly a $750 million difference in cost. It's a big difference.
What about situations like power fluctuation or extreme weather? Advancing global warming, we're dealing with more extreme weather situations, and with the introduction of more wind and solar to the grid, how would molten salt reactors respond to deal with power fluctuations and for the extremities of weather we're coming into now?
For a growing renewables grid, this gives you the exact flexibility that they need. Typically, you can only go up to about 30% renewables on a grid. With this flexibility, you get up to 70 or 80%. And the same goes for extreme weather scenarios or power fluctuations. When you have this storage of thermal high temperature heat as energy, You can use it to kickstart turbines from a black start. You can use greater flexibility to get over these scenarios.
From ThorCon's perspective, we're targeting the developing world and intending to be the dominant power source on the grid. So our basic design have to be able to load follow, have to be able to do black start, be first one that turns the grid on, the last one that comes off. And if you look at history, I think you'll see that nuclear power plants, even the old LWRs, are the ones that are able to take the weather the best. I mean, they are not affected by hurricanes or tornadoes. The floods have to be pretty extreme and not difficult to design to handle even more extreme cases. So for extreme weather, I think nuclear power plants are actually the best answer.
We've had reactors that have stayed up through hurricanes and all the others didn't. We've had big freezes in the Northeast, and the nuclear reactors were the only power source that stayed on in those scenarios. We have had earthquakes that the reactors were not at all damaged, and the regulations shut them down. And when the regulations shut down a power source, that means people die because they don't have medical care. They don't have emergency services. So yes, we all have the goal of operating through that. And if you think about it, for a lot of the reactors, the fuel is not damaged, even if it's solid. For a liquid fuel, certainly the liquid fuel is not damaged because you shock it. It just doesn't happen. And that's what's viewed as the most vulnerable part of the plant, is the fuel damage.
Is it possible that our older nuclear infrastructure can be overhauled to replace worn-out reactors instead of decommissioning them? And along these lines, could coal and gas facilities also be replaced with advanced reactors?
The easy thing is to reuse the site. You've got the cooling water access, you've got the land area, you've got the transmission lines, and you come in and replace the rest.
It depends on the lifetime of the turbine. Remember I said that 85% of the cost of a nuclear plant is not the nuclear island part, but the other part. So could you use it? It depends on the economics and the age of those turbines and how long they're going to last.
China's been building hundreds of coal plants over the last decade or two, and it's very easy to reuse those turbines for a molten salt reactor.
I might note on that context, the United States is not allowed to build anything but large light water reactors in China. So that market is not really open to us. Unless, per se, you can bring a reactor in, drop it in, and let them operate it. But if there's any possibility that they're going to learn the technology of building the molten salt reactors, you're not allowed to do it.
Does that mean that there's going to be less decommissioning going on?
When you're talking about decommissioning reactors, you're really talking about the developed world, the U.S. and Europe and Japan. And I think politically, you won't be allowed to just abandon them and close the door. I think you will have to actually decommission them and tear them down. It may not be necessary technically, but politically it will be a flat requirement. And whether you have MSRs or not, I think they're going to have to take them down eventually. But eventually could be after 80 years' life. Newer reactors, the decommissioning process is a lot simpler. And I know it is for ours, and I'm guessing it probably is for everybody else's as well.
Our reactors are being designed so that you can replace components and basically use the plants indefinitely. The fuel basically outlasts the reactor components. The reactor vessel is probably the shortest lifetime component that we have, at least the part that's near the core, like the CANDUs are doing right now. And so those are essentially a very long life capable plant because you're replacing the components that are getting damaged. And one other little tidbit is once a reactor is started up with the fissile fuel, all the stored nuclear fuel at those old sites are fuel for our reactors.
Somebody expand on proliferation concerns with molten salt reactors as distinct from light water reactors.
Molten salt reactors is a very large class of reactors, at least as large as solid fuel reactors. So the proliferation concerns is very much specific to the design, but with molten salt reactors we have more design flexibility, so you can design reactors that are even more safe than light water reactors. In fact, both the UK and the US, when they went to look for making a more proliferation-proof reactor than a light water reactor, both ended up with molten salt reactors. If you look at history, commercial nuclear reactors have not been a proliferation risk. Everybody that's developed nuclear weapons did not do it through commercial nuclear reactors. If a nation wants to, the technology is out there, the knowledge is out there, and it takes some pretty aggressive moves to prevent a nation that wants nuclear weapons from getting them. It is possible, theoretically, to modify a reactor, but it's no trivial task. In fact, it would be easier for such a nation to build a reactor specifically for the purpose of making weapons-grade material. That's simpler than taking a commercial reactor and modifying it to create your weapons material.
That country is going to need a multi-billion euro, dollar, whatever, reprocessing facility to get high-purity materials to be able to make a bomb. They're much better off to use a centrifuge out of uranium if they were going to do it.
Keeping in perspective what the theme of our show is, coming atomic revolution, do you all have anything to say in conclusion?
From my perspective, the big battle is to get the next generation nuclear stuff out in volume rapidly before we end up with 10 times as much coal burning as we have today. 6/7 of the world has very little electricity, but they're building it fast. China built a grid as big as the United States in 15 years. India, Indonesia, other countries will be following soon. Can we get it done in the next decade and get them out there in high volume so that the dominant source of electricity is nuclear rather than coal?
We have a customer on board in Canada, New Brunswick Power, with a plan. We know what needs to be done. There's no major hurdles. It's cash. Cash is what's going to make this go faster.
I agree that we have to get the electricity grid done, but that's not sufficient. The electricity is a minor part of CO2 concerns for the environment, and so you need to move into that process heat to start replacing transportation fuels and manufacturing heat sources. Use that heat because those are the kind of places that produce the most CO2 and a lot of the pollution, and shipping.
If any of our listeners would like to invest in your companies, how would they go about it?
Contact us through our website, ElysiumIndustries.com.
It would be ThorConPower.com. We'd love to talk to you.
MoltexEnergy.com. We are actually launching a crowdfunding campaign in about a fortnight, in about 2 weeks. So it'll be a bit easier for people to invest. The minimum amount is £1,000, so about $1,300. That'll be through a platform called Shadow Founder. So that you can find that on Google.
Okay, thank you guys.
You're welcome.
And now for our final thoughts. Nowadays, the atomic revolution and even the scientific revolution have been looked on more and more as a folly and a failure. Nothing could be further from the truth. The very fact that our problems are so great means that we can never have enough technology.
The question of whether technology can solve our problems is yet to be resolved, but one thing is certain. Without more and better technology, we will be doomed to fail. The only way through the predicaments we face is to move forward. We'll need even more energy in the days ahead, and virtually all of it has to be carbon-free. The best way we can get there is nuclear power.